Okay, look what we have here. We have two new theorems, Rolle's and MVT. Think about what we know already, guys. What two theorems do we know? Do you remember we know IVT, which said basically if I go on the number line from 5 to 10, I'll hit everything in between so long as the function's continuous, right? We need to make sure we have continuity. We have EVT that said if a function's continuous on the close, we're guaranteed a max and a min. Okay, Rolles now in MVT are going to tell us something different. I'm going to focus just on Rolles for now, and then we'll go to MVT. So I'm going to walk you through the steps and kind of build up to what Rolles is saying. So look on Roman numeral 1, we have Rolle's theorem. It says draw a differentiable function. So right away, if I'm thinking differentiable, I want you thinking two words, smooth and continuous. No corners, cusps. We can't have vertical tangents. We can't have discontinuities. Remember also, if we have differentiable, that implies that it has to be continuous. Okay, so it says start at 1, 3 and end at 5, 3. So basically, we're starting at the height that we're ending with. So go ahead, take a second on your own and draw differentiable functions. Remember no corners or cusps or discontinuities that start at 1, 3 and end at 5, 3. You could draw a lot of different ones. I'm going to do this. Watch the pen, it's going to disappear, but you could have done something like this. Okay, you could have gone this way. You really just can't have corners or cusps. So I start here and end here. Okay, if you have something different, don't erase it, just leave it. Now, is there at least one point where the derivative is equal to 0? Well, what do we know about derivative equal to 0? Isn't that a horizontal tangent line? I see one right here. Is there at least one point? Sure. Hey, what if someone drew this? What if I started at 1, 3, ended at 5, 3, and did this? Do you get why I said is there at least one point? Because now I have two. Okay, so depending on the graph you drew, you could have multiple horizontal tangent lines. Okay, so is there a point where the derivative is 0? Is there at least a point? Yes. Now, can you draw a differentiable function that starts at 1, 3 and ends at 5, 3? Again, try this on your own. And does not have any hills or valleys. So what I mean by that is, look right here. I went up to come down. Here I went down, up. I went up, down, and then up again. Can I draw a function that starts at 1, 3, ends at 5, 3, is still differentiable, no hills or valleys? Go ahead, take a second. This is what you could draw. That's it. Is there at least still one point? So if I still start where I end, is there at least still one point where the derivative is equal to 0? Sure. At all of the points, the derivative is equal to 0, right? What's the slope of a horizontal line? 0. So it didn't matter if I put a hill, a valley, or if I went straight across. Okay, and that's basically what Rolles is saying. Remember over here with IVT and EVT, we had to say that F was continuous. Okay, look at how Rolles is starting out. A lot of these start out this way. So if we want F to be continuous on the closed interval, okay, now here's the new part. We also need differentiability on the open. Okay, notice we don't have to be differentiable at A and B. It's the open interval. So we have this condition. Okay, there we are. Okay, we have this condition, continuity on the closed. We have differentiability on the open. So there's one, there's one. So two conditions. So they're saying let F be continuous on the closed, differentiable on the open. And then here's our third condition, if F of A equals F of B. Well, isn't that what we did? Let's look back up here real quick. F of A equals F of B. That means where you start is where you end. F of A is equal to F of B. So if I start where I end, there is at least one number C such that the derivative is 0. Okay, so it's saying if we have continuity, so there's no gaps, no corners or cusps for differentiability. If I start here and end here, right, we drew this case, there at least one value where the derivative is 0. That's Rolles. Notice it's not saying, hey, tell me when the derivative is equal to 0. It's just saying there has to be a point where that happens, okay? We saw in 3.1 all the importance of derivative equal to 0. Remember that was a critical number and that had potential to be absolute max and min. So the derivative equal to 0, we're going to use a ton in this chapter. Okay, now I want you to understand, I just don't want you memorizing this. Why do we need continuity? Why do we need differentiability? Why do we have to start where we end? Okay, so let's take this apart and say, well, what if this wasn't here? Okay, so what if I started here, ended here? And what if I had this? Okay, so what happens if I don't have the first condition? What happens if f is not continuous? Well, what would that mean? Doesn't that mean the maximum is not guaranteed to exist? If the maximum isn't guaranteed to exist, how am I supposed to draw this horizontal tangent line, right? I can't. We're up here, because I had continuity and differentiability, I could draw the tangent line because that point existed. I want to be able to draw it here, but I can't. So here's a case why we need continuity. Now, why do we need differentiability? Let's say I start where I end again. Let's say I start here and end here. What if I have this? Functions is not differentiable there. Do you see that because we have a sharp turn? The function's not differentiable there. We can't draw our tangent line. We don't have a derivative equal to 0. Okay, so that reason would be, what happens if f is not differentiable? Why do we need this to happen? Because f prime can't equal 0. Because the derivative doesn't exist there. Okay, the last case says, what happens if f of a is not equal to f of b? So what if I don't start where I end? What if I'm here and then I can go 1, 2, 3, 4, 5? What if this was my function? Are we guaranteed to see a 0 slope, a horizontal tangent? Do you guys see that we can't guarantee that? Remember, the whole point of Rolle's theorem up above is to say, if we have continuity, if we have differentiability, if f of a equals f of b, this is our conclusion, right? That's what we're concluding. Let's use a different color there. If that's what we want, we can't guarantee in this case. Like, look at, if I draw a tangent line here, it looks like this. None of these tangent lines are 0. The only reason we are guaranteed 0 up here is because if I start where I end, at some point I have to go up to come down, or I could go straight across. Okay, here we just kept increasing. Okay, so that's why we need those stipulations. Now let's look at a question. Hey, a lot of your questions are going to say the beginning part. Determine whether rules can be applied. And really, that's what we need. Now, this one's going a little further, as does the one in your book. And it says, okay, if we get a derivative equal to 0, can you tell me what value caused that? Okay, so this is expanding on it a little bit. When you do roles, I need you to list the conditions. We have continuity on the closed, differentiability on the open, and the output in the beginning is the same as the output at the end. So let's look at this first one. We have an absolute value function. Is f continuous? Sure. We don't have any gaps, so f is continuous on 0, 6. Now, to find out if we have differentiability, you need to take the derivative. Absolute value is a little weird. How about we analyze the graph? Let's look at these shifts. Do you see the x minus 3? That means I go 3 to the right. Do you see the 3 added on? So normally, if you want to rewrite this, it normally would look like this. It would be negative x minus 3, that's a 3, plus 3. Okay, this might help you to see the shifts. So what it does is it moves 3 to the right and 3 up. Okay, so we know we have a point here. The negative in front, instead of taking the absolute value up, it's going to reflect it down, and that we have a slope of 1. So if you can imagine just going down 1 over 1, we're going to get this. Okay, and this should have went through 0. We'll just make that line a little thicker. Okay, so we really didn't need all those details. There's the sketch. Do we have differentiability? Now, remember, if I'm looking at this piece, I'm good. But they're asking me to look between 0 and 6. Do I have differentiability there? No way. We have a sharp corner there. So f is not differentiable. Remember, it had to be differentiable on the open. So f is not differentiable on 0, 6. Therefore, one of our 3 conditions is not met. Rolls fails, we cannot go on. Therefore, this is shorthand for therefore. Therefore, Rolle's theorem does not apply. And the only good news about this is there's nothing else for us to do. Okay, remember if we looked at a different piece, guys, like if we went from 6 to 7, let's say, we could apply rules because we didn't have the corner in that piece. Okay, let's go on to these. So we have this function. It's a quartic. Is a quartic continuous? Yes, we have no 0 in the denominator. We have no radicals. So this is totally fine. So we can say that f is continuous. Remember, try to anticipate my words as we go through this because I really want you to memorize this theorem. F is continuous on the closed. Now, the only way you're going to know about differentiability is to take the derivative. So let's go ahead and do that. The derivative is 4x cubed minus 2x. Is that function differentiable? I'm sorry, is this function good for all x's in this region? Sure, this function's good everywhere. There's no 0 in the denominator. There's no radicals. So we can also say that f is differentiable. And f is differentiable on -2 to 2. Okay, our next piece is we have continuity, we have differentiability. Now we need to find the output at -2 and 2. So we're going to go ahead and sub a -2 into the function. So we're going to have -2 to the 4th minus -2 squared. What is that? 16 minus 4, which is 12. And we're going to do the same thing for f of 2. And look at it, it's going to be the same thing. You can tell because they're both raised to even powers. Okay, so we have our checks. We're good. We have continuity on the closed. Let's use a different color. We have differentiability on the open, and we have f of 2 equal to f of -2. Let's write that down. We did f of 2 equal to f of -2. Okay, so look at all these good check marks we have. There's our conditions. Now we can just say we've met enough of the stipulations. Now we can say, therefore, Rolle's theorem can be applied. And why do we care about Rolle's theorem can be applied? What's the conclusion? All of this is just building up to say that there is at least one C value in the interval -2 to 2, such that, what's the big conclusion with Rolle's, guys? Try to remember that activity we did, such that the derivative at that C value will be a 0. Okay, this is normally where the problem ends. All we did is we guaranteed that we'll have a derivative equal to 0 here in this problem. Now up above, I told you they asked a little extra, and they said, can you find the value when the derivative is 0? Sure we can. So let's take our derivative, which was 4x cubed minus 2x, and we're solving for c, so I'm just going to go ahead and put a c in right away. And let's factor out a 2c. Okay, now that we have this, we can go ahead and solve. So we're going to have c is equal, our solution set would be 0 plus or minus, maybe you guys need to see this step right here. If you set this equal to 0, you're going to get 2c squared minus 1 is 0, 2c squared equals 1, c squared is 1/2, and then take the square root, plus or minus. Okay, so that's how I'm getting that. It's 1 over root 2. Don't forget, though, that we have to go up here and say we had a domain to begin with, -2 to 2. Are all of these answers in -2 to 2? Sure, so we're good. If not, we wouldn't include them. Okay, so you want to make sure you check to see if they're in the domain, which they are, so you're good. Okay, so this is the idea with Rolle's. If you can go ahead and try the next one on your own, try to stay like a step ahead of me and see if you have the theorem memorized. Okay, the first thing we need to know about continuity. Look at this function here. We have no denominators. This is the cube root, but we can take cube roots of negatives, so we have no stipulations. Before we go on, though, let's take the derivative. So we know f is continuous. The derivative is going to be 1 minus 1/3 x to the -2/3, which is going to be 1 minus 1 over 3 x squared cube root. Okay, now do you guys see we have an issue? So let's start listing this, and we already said f is continuous, right, on 0, 1. But now we have an issue. As I'm looking at this domain here, as I'm looking at the derivative, don't we now have an issue? X can't be 0. Right here, x can't be 0. Let me move up. And look at zeros here. So the question is, does this Work with roles. Does it still meet the conditions? Well, look what f had to be. Look left. F had to be differentiable on the open. Remember, we don't need differentiability at the endpoints. So is this function differentiable if I make this open? Sure, because once I make it open, 0 is no longer included. So it's tricky. It looks like 0 is an issue, but we didn't need the function to be differentiable at 0. So that's why we're okay. So f is differentiable because we know our theorem so well that we know that that's open. Okay, now we have two checks, right? We have differentiability and continuity. Now we have to find the output at the endpoints. So f of 0 is 0. You guys can see that. And f of 1 is going to be 1 minus 1, which is 0. So we have f of 0 equal to f of 1. Okay, roles is a go. What's the conclusion now? All we did was prove we can use roles. Then we're going to write exactly, well, similar to what we wrote on the left. Therefore, Rolle's theorem can be applied. Again, try to memorize this. What does that mean? That means that there is at least one C value in, what's our domain? 0 to 1, such that, what's the big deal with roles? It's that the derivative is equal to 0. They asked us to go a little further though. Remember they said, okay, we get the derivative is 0. Now tell me where that occurs. So we have 1 minus 1 over 3 x to the 2/3. This was our derivative. We're saying, let's find the x that makes this true. Let's take the fraction to the other side. Let's go ahead, I would say cross multiply. Let's divide both sides by 3. And you know what, since we're solving for C, we can go ahead and make these C's. Okay, we have to raise both to the 3/2 power to get rid of the 2/3. This is going to give us C equals. So what you're doing here is you're taking 3 to the 3rd power, which is going to be 27, and then you're taking the square root of 27. Okay, also because we're taking the square root, we're going to write plus or minus. So 1 over the square root of 27. We can clean this up a little bit. Now, is this our answer? Do you guys remember the stipulation we had to look at? We have a restricted domain. We are only between 0 and 1. We don't want this negative. So even though we found two C values, we say, well, what does the theorem say? The theorem says that there's a C value in this region. So we need to only keep the positive because the other negative value is not in the restricted domain. Okay, so that's what Rolle's theorems are going to look like. Let's look at the last one. Here's a little application of it. Particle motion. So if a particle moves along a line so that its position is given by s of t, and you can see the function, is velocity equal to 0? Well, how would we even know that this is Rolle's? Well, what I want you to do, if you remember in the particle motion section, is if they give me position and they ask me about velocity, I'm going to interpret this to say s prime of t is 0. Now I hope that's a red flag for Rolle's. Let's look back at Rolle's again. What did Rolle say? If we have continuity and differentiability, and if the outputs are the same at the beginning and end, then the derivative of f is 0. And what are they asking for? The derivative of the given function to be 0. That's how we'll know this is Rolle's. Also, look, they give you a closed interval. Okay, we need that also. Okay, so first condition, we need the given function to be continuous. Look at, that's a quadratic. We're good. So f is continuous on the closed. How do we know if we have differentiability? Well, we need to find the derivative. 2t minus 4. That's a line. We're good. So we can also say that s of t is differentiable. On the open. Now we need to find the outputs. Because my interval goes from 0 to 4, I'm going to find s of 0 and s of 4. S of 0 is 3. Look, if you sub a 0 in here, gone, gone, 3. Now I'm going to go ahead and find s of 4. S of 4 is going to be 4 squared minus 4 times 4. Well, that just wiped itself out, which is 3. So we have s of 0 equal to s of 4. Here's our three conditions. Continuity on the close, differentiability on the open, output's the same. Therefore, now what does Rolle say? Therefore, well, I already wrote therefore, we don't have to write it again. Therefore, Rolle's theorem can be applied. And what does that mean? That means that there is at least, in this case, we have a t value, right? We can, okay, they said is v of t equal to 0. So there is at least one t value, and then we have to say where is that located? Well, it's going to be between 0 and 4, such that, now here's where you have to be careful. They asked for velocity, right? But this whole time, oops, I did not mean to do that. They asked for velocity, but this whole time we've been referring to it as s prime. So you want to make sure that you catch that and write that. So there is at least one t value such that s prime, which is velocity, is 0. Okay, that's going to wrap up Rolles. I'll see you next time on MVT.